All right, yeah, thanks for the introduction. Thanks everybody for coming today. I'm going to talk to you today about an interface that I've been working on between R and Bioconductor and this Hail platform for doing genomics. It's Spark-based. So Hail is this platform and actually defines a language of its own for doing distributed genomics on Apache Spark.
This is the microphone, sorry.
Okay.
I see.
They both work, but
Okay, what should you use?
all right.
Whatever. You can give it
I'll
to
just
me.
put, okay.
Yeah, sorry.
I'll use this microphone now. Yeah, so what does Hail provide? So Hail provides a table, as pretty much any data analysis tool would need for analyzing, for manipulating tabular data, and then it incorporates that into a larger data structure that closely mimics other data, a similar data structure in Bioconductor, and it's generally designed to be efficient. It takes full advantage of Spark, and it can even pass down many of the operations in this Hail language are actually implemented in C++, sort of sharing memory with the Java virtual machine. So they've really gone through a lot of effort into making this a scalable platform. Really kind of impressive from the computer science perspective. And their idea is that you should be able to interface with Hail not directly in Scala or Java or by writing this bytecode yourself, but through a higher level language like Python or maybe soon R. And so in the R world, there's a very similar platform to Hail, although it's much more sort of mature and more of a diverse ecosystem. And this is Bioconductor, and it was started in 2002, so it's been around a while. It's currently led by Martin Morgan, who will be talking a lot more about Bioconductor in a couple hours, so I'm not going to go into any more detail. This doesn't count as credit for that talk or anything, so have to go to that one. But it has a lot of packages, and they're all integrated on top of a set of infrastructure packages that unify everything and ensure interoperability between all these different packages developed by people across the world. And they're based on these key data structures. And what the sort of most key data structure for most of the statistics that are done with Bioconductor is something called the summarized experiment. But this is the same data model as what Hail calls the matrix table. And essentially you have a sort of stack of matrices that are some feature along the row and some sample along the columns, and these hold assay measurements, like summarized assay measurements. And then you have annotations on the features or annotations on the samples, and each of those are in the form of a data frame, as well as additional metadata. So the Hail R package builds on top of Hail, which in turn builds on top of Spark. We're currently using the Sparkly R interface for talking to Hail, but we have sort of an abstraction on top of that for sort of conveniently dealing with these Spark objects, and then building out these high-level data structures that implement the same API. They essentially extend the Bioconductor data structures, but implement them in Hail rather than in R. And all of these, of course, are, they provide the same API as everything else. So what actually happens here is that we are essentially compiling a program which we then pass to Hail to run. And so the way this works is by what you would call lazy evaluation, in the sense that we're not, for every single time you would evaluate the function call in R, it's actually just building up a Hail program and not even necessarily sending it to Hail. And so we defer that computation until we can build things up. So if we were to call sort on this object, an eager evaluation, what you would have is you would immediately call Hail, and then you get back the sort of full data set, which might be quite large, and then you would take the head of that afterwards. But with lazy evaluation, you would capture the sort operation, and then you would capture on top of that the head operation, And then you would ask Hail for the sorted head, or the head of the sorted data, and then you'd only have to get that back to R. So it reduces data transfer and allows Hail to do optimizations on its side. And so, yeah, as you maybe know, that R already uses a lot of lazy evaluation for different things. And so you can see how on this y-axis here, it's captured at 1:10. The way it does that is that the arguments to a function call are lazily evaluated, so you can capture the expression. And this shows how you might do that. And this shows how, eventually, once the value is needed, that'll be forced. And there's lots of applications of this idea of laziness. It's been used many times over throughout computing. We just saw provenance capture. You can build up some sort of pipeline, for example, an interactive graphics pipeline that you could operate on. You could do something where you defer an operation, allow it to operate asynchronously, like the promises package. You could optimize over a structure like the Rengen our implementation does. You can build up these sort of compact representations, a representation that hasn't really been fully realized yet. This is an example from actually in a recent version of R. If you do 1 colon, to a trillion or whatever, it won't actually create all those trillion numbers. Instead, it'll immediately return with just because all it's doing is storing the endpoints of that. Similar thing for the way we do compressed lists. So that's where vectors, we don't actually form every single element of a list. We just store a partitioning of a vector into that list, so it's lazy. You can build up queries to databases, and then you can even distribute these queries or these computations across a distributed environment. This is a diagram from Chen and Ripley, I think back in 2001, where they were doing this with Corba. All right, so the idea here is, what we're kind of doing though, is this idea of a deferred data structure. So we have objects that are promises, and what happens when you type this expression, you'll end up dispatching, these are all generics, and so you'll end up dispatching on this promise type, and it'll call down to these promise methods, which builds up this computation, and then just lets us capture that, rather than actually doing the work, and then eventually you'll serialize it to this form, and then this is the Hail language, it's a Lisp-like syntax that you actually send to Hail. And this idea was, the first time I could probably find this was that in this program called Riot, where they did this with, they used S4 to build up these expressions that they could then push down to a database, and that was about 10 years ago. And so here's just a little sort of a philosophical point. So when the goal here and the goal of Bioconductor in general, as it's been developed, is to extend the base R API, because we're trying to do genomics in R and sort of in the most direct way. So we want to enable programmability, definitions, and reuse of data structures. And so we based all these on the base R API. And I think it makes sense for for these low-level interfaces to external systems to also be based in the base R API. And then you can layer on top implementations of various DSLs for doing data analysis, like dplyr or whatever. But those should be layered on top, so you ensure you have full programmability of your system. So in Bioconductor, we make use of a technique called duck typing, where we allow things to be sort of vector-like, or so duck. If it acts like a duck, we say it is a duck. So these allow our data structures to be very generic, because we can put anything that acts like a type of object, say like a vector as a data frame column, or a summarized experiment, anything that acts like a matrix. And Hail R is kind of a hierarchical extension of Bioconductor in this way, where we can have, we have our ordinary data frame in Bioconductor. This is just a generic, more generic form of data frame that makes it easier to put custom vector types into data frames. It's been around for probably over a decade now. And what we've done is we've extended this data frame with the Hail data frame, and we can also put in these Hail promise objects as columns, and all of these things are tied to the underlying Hail table, so that we can operate at the column level, but also for tabular operations, we can pass those directly at the high level to the Hail table for optimization. I mean, a big problem with optimization, of course, is do you do it at the low level or the high level? This gives us some flexibility in the granularity of the optimization so that we can optimize at different levels. And the same goes for extend that idea for the Hail summarized experiment object. So we can, this is just some examples now of, you can pass in one of these tab separated files, and you can call this read Hail data frame from text function, and this will tell Hail to read in this file. And what you get back is a data frame, but it's actually in Hail. And you can also copy an existing R data frame to Hail in that way. And then you can get it back out again. You type this, and you can see that these columns are actually promises. So what's actually happened here is it's only queried Hail for the first 4 rows here of the data. And the same, you can do the same thing. You can get a column out, df $ID or whatever, and you can get out the data that way too. So it's flexible. It's implemented at different levels of granularity. And here you can kind of glimpse into what the compiler has done. So you can get out the expression from the promise and then coerce that to character, and you can see that you're getting a field called ID from this row structure in the Hail table. And once you have this duck typing and this abstraction, it now allows you to use all sorts of different forms of evaluation. You can evaluate things in a mixture of different systems, all in one integrated way, and even eagerly. So you can have Hail promises, you can have promises in Solar. This is a package I made a couple years ago, the R Solar interface. You can have an ordinary all R vectors, maybe even alt-rep-based all R vectors that are going off and doing something. And you can bring all these together in this abstract framework to enable this. And it's still a little bit complicated how you'd actually achieve some of these computations. There are different approaches based on different cost models. Who do you move the data to do the computation and stuff like this? And you can get fairly fancy with that. But just a little bit looking forward here in terms of sort of building up an intermediate representation of the R language. If you were able to do this sort of thing and build up these expressions behind the scenes, you could build up a sort of more abstract version of R, and then you could map, say, the bracket here down to, if you're doing bracket 1 to 5, you can map that down to head, and maybe head translates into something more, and maybe you can coalesce operations where you can say, well, if you're taking the head of the sorted data, you can now just do a partial sort, so you can do some optimization there. This Apache calcite framework is kind of interesting, that it allows it kind of provides an optimizer that you can have. You can reuse a reusable sort of optimizer that supports multiple backends and has a way to coordinate those things. And so then you could translate that intermediate representation down to different backend languages. And so we can kind of try to generalize some of this stuff. All right, so I'm just going to acknowledge that Javier and Kevin from SparklyR, from our studio. They were a big help in getting SparklyR working well enough for me to use it for this work. And Samuel our studio's been paying Samuel to help out with some things, and the Cotton Seed has helped out. He's the leader of the Hail project, and he's kind of helped me get started with stuff. But that's all I had. Any questions?
Thank you, Michael. Are there any questions? You can circulate the... Yeah, there is one in the back.
I want to know who would call their kid cotton seed. Sorry. The actual question is, how would you go about debugging, since if you rack up your commands and then pass them off to Hale, what would you do in terms of debugging it?
Yeah, so I mean, these functions are all, implemented in a way that, unless if you wrote your own code on top of this, a lot of these functions would, throw the ordinary, exceptions and things like that when things went wrong. So it's really just about, these are lower level functions that are being implemented that user code would be calling. So ideally the users don't have to debug what goes on down in Hail. It's just like how a user hopefully doesn't have to debug what's happening in C when R is implementing these things. So ideally, we can capture all the common errors and sort of fail early before they get down into Hail land and they get a weird exception out of Hail.